For the reflection quiz. Number one, draw a light ray that hits a flat surface. So here's my flat surface, and we need a light ray that is coming in and hitting it like that. Okay, there is my light ray. Now, we want to draw the reflection and the normal. The normal, remember, is the 90-degree perpendicular line to where it hits. So I draw 90 degrees, and it's like, there's the normal. We call this the incident ray, and the incident angle is going to be this one right here, theta sub I. A lot of people take it to the surface, and that is wrong, wrong, wrong. Do not do that. And I measure this to be about 35 degrees. The reason why I have to measure it is because when I draw the reflected ray, it's going to have the exact same angle if life is perfect. And right now, life is perfect. I have a full cup of coffee in me, and there's a thermos of more next to me. We call this then the reflected ray, and this is the angle of reflection, theta sub R. It's also going to be 35 degrees. So that is question number one. Number two, what's the relationship between angle of incidence and angle of reflection? I would write down theta sub I is equal to theta sub R. Number three, what is the relationship between the object distance and the image distance of a flat mirror? Let's see here. DO is a variable for object distance. You might see it as a capital DO. Either way, I've seen it both ways. And that is going to equal the image distance. Whoop, let's get a capital D there. Those two distances are the same. But I will say that the image distance is going to be negative, because the image for a flat mirror is always behind the mirror, and that's going to be negative locations. The object distance is always going to be in front of the mirror, so that's always going to be positive. But the numbers, the magnitudes are the same. That is question number three. Question number four. What's the relationship between the object distance and image distance of a concave mirror? Number four, we have the Fedoti equation. The F is the focal length. That is a measure of how curvy the mirror is. DO is the object distance. DI is the image distance. It does not matter if you have these in centimeters or meters or inches. They are all fine. It's just that if one is in inches, they all got to be in inches. If one is in centimeters, they all have got to be in whatever I just said. Okay, number five. It takes 4 seconds for a person to hear their echo off of a flat cliff. How far away is the cliff? 4 seconds. So here we have the person, here we have the cliff. The sound goes forward and back, and the entire time is 4 seconds. One of the things that I will always tell you is the speed of sound. The velocity of sound, we're going to say, is 340 meters per second. Now, that's just kind of a typical average. As you heat up the air, as you make it more humid, as you go to higher elevations and it gets thinner, you're going to have different numbers, but 340 is a common number for it. Okay, so we have the time of travel. We have the velocity as it travels. We want to know something about the distance. Now, the question here is asking us for the distance to the cliff. Distance. We better put a delta x here, because that's what we used first semester. Now, what's this delta x, though? You got to be careful. We have a distance here that the sound travels, but then we have the distance just between the person and the cliff. That is what we are looking for, the delta x. Just this distance, not the forward and back. So, this time is forward and back. We don't want to do that, so we're going to scratch that off, and we're going to cut half of it. We just want half of that travel time to the cliff, so that we can measure the distance to the cliff. So we get the equation, v equals delta x all over t. The V is 340, as we've said. The delta X is what we're looking for, and then the 2 seconds goes on the bottom. Multiply both sides by 2, we get 680 meters is the distance to the cliff. That was question number 5. With that in mind, would you please look at question number 6, give it a try on your own, ready, set, go. Yeah. Okay, so there's a diagram of this situation for problem number 6, but I have not written down the time. What number should I put down for the T here in this question? Adam, what do you think? Yep, I heard a whole bunch of people saying that. That was just grand. 3.5 seconds. So V is equal to delta X all over T. V is 340, and then we have the delta X all over 3.5. What is that answer, Chris, when we multiply both sides by 3.5? What's the answer for the 3, 4?
I don't know.
Okay, 3.5. Would you please take out your earbud and put it in the pipe? Thank you very much. So we get 1,190. The pipe is down there by your left foot. Thank you. Okay. Questions on number 6. Number 7, a large building is 100 meters away. How long will it take a person to hear the echo off of it? So here's the tall building that you're going to hear an echo off of. Here you are, and it is delta X is 100 meters. That's from the person to the building. We want to know how long it takes the sound to go there and back for us to hear the echo. We want to know the total time. The velocity during this entire time is still 340 meters per second. So think about how you're going to work this one out. I told you. And I will always tell you. It might vary a little bit from story problem to story problem. I might say 360 sometimes, but 340 is today. Okay, the equation, V equals delta X all over T. V is, come on pencil, 340. The delta X is 100 on the top. The T is our unknown. Do not just simply divide both sides by 100. It's more complicated than that. One way of doing it is to make it a proportion and change the diagonals. We've done that lots of times. So you have T is equal to 100 divided by 340. What's that? Let's check that out. 100 divided by 340. 0.294 seconds. But is that really our answer?
No.
Max, what do we do?
You need to multiply by 2.
Yep. We only did the delta X being 100. So this T that goes along with that is just the time for your sound to go to the building. Now we got to retrace our steps and go back, and we assume it's going to take the same amount of time. So we multiply this by 2, and we get 0.588 seconds. That was question number 7. Would you please do number 8, which is very similar? Do number 8 right now. When you're done, turn to your neighbor and see if they get the same thing. This is number 8. What do I write down first, Christian? I drew the picture with all the information that we know so far. Okay, let me back up just a little bit. I'm assuming that Christian started off with this equation and put in the 340 for the velocity, the 56 for the delta x, and the t down there. And then I assume that he switched the diagonals. And so he gets that so far. That's absolutely correct. Andres, when I divide 56 by 340, what do I get? Okay, Thomas? Well, let's see here. 5 over 30 would be 1 over 6. And so, what did you say, Thomas? 0.16. And yes, that is approximately what I was looking for. Yep. Okay, now, that is the time to go the 56 meters. As Davis just mentioned, we got to go from the 56 to the building and the 56 back again. So we got to multiply by 2, and we get 0.32 seconds. Now, I don't know if I was going to remember that or not, Davis, and so I'm going to assume that, no, I was not going to remember that, so here's your reward for keeping track of me. Thank you very much. Questions on number 8? Okay, that is the math review from the first little lesson on flat surfaces. Please open up your packets at this time and look to see, is there anything else from flat mirrors that you think could possibly be on the quiz? Go ahead and look at that right now. At this time, you should be opening up your packet. It looks like this. I'll be glad to give you a new one if you need. We're going to be doing this multiple times during the lesson, so you do need to have it out. Anybody want a new one? Somebody name one thing that might be on the quiz about reflecting from the first couple. Chris? Okay. The equations that we just did. What else might be on the quiz about this reflecting? The first, let's see here. The first lesson went all the way through all of this to locating an image. We did that with a flat mirror. We went all the way through. We did that homework assignment. Okay, so day 122, 121 and 122. What's going on in those two lessons that might be on the quiz besides the math that we just did? Kaz?
Reflecting, like drawing the reflecting or labeling the reflecting line properties.
Okay, like we did with the first problem there. I drew the incident ray and the normal and stuff like that. Yep. These 121, 122. What else might be on the quiz? Davis?
Like something about like ultrasound machines.
Ultrasounds. How do they make pictures? Yes. Ultrasound and sonar both make pictures with reflections. Christian? Before, we're just looking at 21 and 22. 121 and 122. We'll get to that in a second. Andres? Okay, by where the two visions match up, where the lines crisscross, yes indeed, like the old pirates did, the way back when. Okay, so you got to be aware of all of that. Let's see, echolocation you guys did not mention. Where's those critters? Critters, there we go. Bats and dolphins, maybe even people with echolocation abilities. Nathan, what? Read it. All of it. I'm just telling you different topics that we're not necessarily going over, but you have been responsible for. Okay. Next, we have Day 123 and 124 about concave mirrors. Let's review about that. Question number 10. Draw a ray that initially goes parallel to a concave mirror's axis and then reflects off of it. So that kind of a thing would be shown by a line for the principal axis. There's a lot of chit-chat going on. Could you please stop that? And then we have a focal point, and we have a center of curvature. And if I have the object over here, traditionally we use an arrow as our object. So the first line, we said here, question number 10, a ray that is initially parallel. When it hits that mirror, where does it go? Go ahead and draw that right now on yours. You should have thought or drawn this ray through the focal point. Question number 11, draw a ray that initially goes through the concave mirror's focal point and reflects off of it. So let's get a different color here. Through the focal point, hits the mirror, and when it reflects, it's going to go parallel. Where the two reflected rays crisscross, that's where the image is. Now it's the reflected rays, not the incoming rays. So we're not concerned about that line, and we're not concerned about this line with that crisscross here. Yes, this is a crisscross, but it's a crisscross between an incident ray and a reflected ray. That's not good. We want the crisscross of both reflected rays right there. The base of the image of the object is on the axis. It always will be. So the base of the image is always on the axis as well. This is the tip that gave off these two rays. So this is the tip image right there. So if the tip's down there and the base is up there, that means that the thing is upside down. Whenever you have the crisscross underneath the axis, it's always going to be an upside down image. We call this a real image because the light rays really do travel through that spot. We call it inverted, which is the fancy word for upside down. I can just tell by looking at it that this is shrunk or reduced, shrunk. That looks weird to me. Reduced is a more fancy term for it. It's just simply shrunk, right? There's no ED on that. I haven't had enough coffee today. Okay, next. Number 11 we just did. Number 12, draw a ray diagram for an object 3 focal lengths in front of a concave mirror. Well, that's pretty much what I just did there. Here's one focal length. And I do another one. There's 1, 2, 3. That was pretty doggone close. I'm going to call that done. Does anybody want me to walk through that again? Inverted, meaning upside down. It is shrunk or reduced, meaning a smaller size. Number 13, draw a ray diagram for an object located 1.5 focal lengths in front of a concave mirror. Okay, that is going to be between the F and the C. So here's your principal axis. Here's your curvy mirror. Here's your focal point. And here is your center of curvature. The distance from the mirror to the focal point is always half the mirror to the center of curvature. Or you could say that this distance, the center of curvature is twice as far away as the focal point. They're both true statements. Okay, we want an object located right here. 1.5 focal lengths. So here's 1 plus another half. Okay, drawing this. First ray, parallel to the axis. It reflects through the focal point.
How high do you want to draw the arrow?
This arrow right here? That's given to you. I'll say, here's the arrow, find the image and describe it.
Okay, so it's automatically already there. You don't have to draw the arrow.
Correct.
Good.
It'll be given to you. Once I draw the reflected ray, I'm going to crisscross out the incoming ray. I don't need it anymore. It just might get confusing to me. Next. The ray goes from the top through the focal point at an angle, and it reflects parallel. I'm going to do that again in red. Here's the incoming ray, and the reflected ray is parallel. And then I cross out the incoming ray. I don't want to get confused by this intersection here. That'd be bad, wrong, don't do it. It's this intersection here of the two reflected rays. The object's base is on the axis, so the image base is on the axis. This tip is where the two lines spread out, so where they come together, that's where the tip's image is. And so it's going to be upside down. So I would say that this is magnified. It is enlarged. It is inverted. It's upside down. And it is a real image. The light rays really do travel through that spot. Questions on that? Magnified means enlarged, bigger. Okay, next. We want where it's only a half a focal length away. This is something significantly different. The light rays do not travel in the same manner in this regard. I should say that the way that you find the image is dramatically different. So here's the focal point, here's the center of curvature, and we have the object halfway between the focal point and the mirror. So that's the situation that the story problem is asking for. The first line is exactly the same as before. Parallel line goes through the focal point. But that's where similarities end. We cannot have a line go from the tip through the focal point and still hit the mirror. So that little rule doesn't work. But I think to myself, if the light did go through the focal point, through that spot, and then hit the mirror, it would reflect parallel. So once I draw the reflected rays, I scribble out the incoming rays. And Kaz, what's your question?
It's just like doesn't work.
They don't actually cross each other, but it looks like they came from the same spot. It looks like this one came from somewhere back here. This ray looks like it came from somewhere back here. Now they crisscross. They don't really crisscross, but it appears that they came from that one spot crisscross, and so that is the image tip. The base, once again, is still on the axis, and so in this case, the image is right side up. Whenever you have the crisscross above the axis, the image is always right side up. Right side up. I don't know a fancy scientific term for right side up, like inverted is upside down. I don't know what the... Verted, just plain verted. I don't doubt that. Okay. It is enlarged. It's magnified, in other words. And the light rays do not really travel behind the mirror. So this is not a real image. We have to use our imagination. Virtual, like virtual reality, is our computers giving us an imaginary world. A virtual image. Virtual images are always right side up. Real are always upside down. Virtual images are always right side up and always behind the mirror. They are not always enlarged, though. Sometimes they're bigger, sometimes they're smaller. Okay, that was question what? That was question 14. Number 15, a concave mirror has a focal length of 10 centimeters. The object is 4 centimeters in front of it. find the location of the image. We're going to use Fedoti for this. We could draw a really good ray diagram if we wanted to, but that's a pretty imprecise way of doing it. Okay, focal length of 10, so I replace the f with 10. I replace the DO, the object distance, with a 4, and then I'm going to solve for DI. You could do common denominators if you wanted. I just like to have the habit of doing decimals. Sometimes it's not the easiest way. I think in this case probably finding common denominators might be a little bit quicker, but it depends on your own personality. Okay, I'm going to subtract off 0.25 from both sides. I get negative 0.15 is 1 over di. And then I flippity-flop everything. I need to flip this side, so I'm going to flip this as well. So 1 over 0.15 is going to be di. Get out the calculator. 1 divided by 0.15 is equal to 6.6. Let's check, does that make sense? We have a mirror, we have the focal length being 10, and it's located 4 away, so it's much closer. We just did an example like this where the rays crisscross behind. So yes, a negative number is the appropriate expectation, showing it's behind the mirror. With that in mind, would you please do number 16? Concave mirror has a focal length of 10. An object is placed 4 in front of it. Find the... Wait, hold it. That's the exact same thing. Skip on to number 17 then.
Oh my God.
Maybe in future years I will have a different question there, but right now in this year, in the fine year of 2020, we have the same numbers. So we're skipping it to going on number 17. Check your work with mine. That was question number 17. Okay, and the next one, we're trying to find the focal length, so we're looking for the f. 1 over f equals 1 over do plus 1 over di. The f is what we're looking for, so it stays a letter. Do for number 18 is 10. And the di is 4. So we have 0.1 plus 0.25. 1 over f is 0.35. I flippity-flop everything. Now I flip that side, and so I'm going to flip that side too. And I know there's going to be around 3. 1 divided by 0.35. 2.8. That's kind of around 3. Okay, so looking at days 120, 123, and 124, those are the 2 days that we looked at concave mirrors. What other kind of topics would you need to be concerned about maybe being on the quiz?
The law of reflection.
That was in the previous set. Okay. Yeah. The solar cooker that the teenager showed, and I showed you a solar fire starter.
The transition like a convex and concave here.
Yep. Here we have the radio telescopes and the microphones and the satellite dishes, the whisper dishes. Question would be, what kind of a lens would be used for a whisper dish? What kind of a mirror would be used, or reflecting surface would be used for radio astronomy? Here we have a telescope. What kind of mirror is used in a telescope to make things bigger? Those would be good questions. Okay, next. Days 125, 126, convex mirrors. Number 20, draw a ray that is initially going parallel to a convex mirror and then reflects off of it. So, once again, we have the axis and the convex bends towards the observer. Okay, so the first line, parallel. Think to yourself, how does that reflect? I'll give you a hint. The focal point is there and the center of curvature is there. It is going to reflect. Think of this as a cement wall that you're throwing a ball against. How does it bounce? It's going to be bouncing up. Does it bounce up from the focal point or from the center of curvature? Focal point is the correct answer. Okay, once you draw the reflected ray, crisscross out the incident ray. Next, the ray goes from the top of the object towards the focal point. It can't get there because the mirror is in the way. It reflects off the mirror parallel to the axis. Crisscross out the incident ray once you draw the reflected ray. They don't cross, but they appear to have come from the same spot. This one appears to have come from somewhere back here. The other ray appears to come from somewhere back here. Where they crisscross, that is the image. So the image is a little person back there. This person's image would be called reduced. It is virtual because the light rays do not actually travel through that spot. It is reduced virtual. It is upright. Oh, there's that fancy word I was looking for. Right side up, upright. There we go. Yeah, that's all I can say. That's fine. You always hear of disgruntled employees. Have you ever heard of a gruntled employee? Okay, next. We just did number 20. We also did number 21. Number 22. 3 focal lengths in front of the mirror. So here is 1 focal length. There's 1, there's 2, there's 3. We'll do the arrow. So the first line is parallel to the axis and it goes away from the focal point. And I'm going to draw the apparent path right away since my ruler was there. The next one goes from the top towards the focal point, but it doesn't get all the way there. It hits the mirror and then it reflects parallel. It appears to have come from somewhere along here. So we have a very small image right there. Okay, now, I can see here it says draw a ray diagram for an object 3 focal lengths in front of a concave mirror. That should be a convex. Sorry. The other two are just too repetitive. So we're going to draw a line through those. 23 and 24 are way too similar to this. I've done 2 of these ray diagrams now. That's enough. Let's go on in life. Oh my goodness, we only have 3 minutes left. Convex mirror has a focal length of 5. Object is 4. Find the location. So, Fedoti, 1 over DO plus 1 over DI. Now, in this case, listen up, this is important. The focal length is behind the mirror. So the 5 is going to be a negative 5. The object is in front of the mirror, so that's a positive 4. The DI is going to be behind the mirror as well, so it better turn out to be a negative number. So we get negative 0.2 is equal to positive 0.25, 1 over DI. Move that over, we get negative 0.45 equals 1 over DI. Flippity-flop everything. We get 1 divided by 0.45 is equal to 2.2. And that's going to be negative. Okay, that's the end of the time for the class. I'm going to keep on going because I'm videoing this. I'm having just way too much fun. So when the bell rings, you guys just take off, but I'm going to do the next 2 problems. Number 27, we have a focal length of, 26. We're going to use Fedoti again. The focal length is 20, and that's going to be a negative 20 because it's behind the mirror. Object is placed 2 in front, so that's going to be a positive 2 for DO. We want to find the image, 1 over DI. So this is going to be 0.05, and this is going to be 0.5. Subtract off 0.5 from both sides. We get negative 0.55 is equal to 1 over DI. Flippity-flop everything. 1 over negative 0.55 is equal to DI. 1 divided by 0.55. So that's going to be negative 1.8 is our DI. 27. Fedoti again. For number 27, the focal length is 5, so it's negative 5 on the bottom. Object is placed 10 in front. That's a positive 10. Find the location of the image. So this is negative 0.2, 0.1, negative 0.3. Flip everything upside down, you get negative 3.33 for your DI. Number 28. Number 28. We are looking for the focal length, so the F stays a letter. The DO is 10. That's in front of the mirror, so it's positive. The image is going to be 2 centimeters, and that is going to have to be negative, behind the mirror. With all convex images, it's always behind, so it's going to be a negative image. 1 over F is equal to 0.1 minus 0.5. 1 over F is negative 0.4. Flippity-flop everything, and we're going to get F is equal to 1 over negative 0.4. 1 divided by 0.4 equals 2.5. Negative 2.5 is your answer, and that's the end. Yes. Or a water bottle holder. I don't remember. Let's take a look. Next to Natalie, behind Sierra.
Take it out. Yeah.
Behind Greece, next to what row? Behind the jean jacket.
What do you want? I can kick it. Moving it over. I have a motion. Yeah, you're ugly. What? If you don't move it with your hand. What's the matter? PVC. I'll break it. Wash my hands. Where did I wash my hands?
Devon.
Hey, don't kick. Do not kick. Use it gently and plastic for people to scooch it over. You can't kick.
Alrighty, folks, please turn to day 128. 128, I believe it is. Whoops. Yes.
Thank you.
You're welcome.
Can I move up a seat so it's easier to see the board?
No, you may not.
Why not? It's affecting my work.
Let's see, you want to be closer to the screen? I'll let you switch with Daryl. That is the option that I'm giving you. Okay. Day 128, while I'm doing attendance, it should look like this on the board. 128. Okay, we have Logan, we have Natalie, we have Mr. Matthews, everybody's over there, that's all full. And we are all here, yoo-hoo! Okay. We are going to review how we do a station model. And then we're going to take the vocab quiz. And then you're going to go to the back and you're going to make 8 station models. That's a project that you should be able to get done in class with no problem at all. And then you have a 13-question homework assignment that you might be able to get done in class, maybe not. Okay, so purpose, I will review and practice all that I've learned in this packet. Let's record this so that people who are missing. Stay 128, page 41.